right, so I work in interpretable machine learning. So what is interpretable machine learning? Well, it's kind of the opposite of black box machine learning. So I just want to define that before I start. So a black box predictive model is a formula that's either too complicated to understand or it's proprietary, meaning that it's someone's secret sauce that they don't want to share. Okay, so what happens when you use black box for high stakes decisions? Well, here's one thing that could happen. You could get several years of extra prison time. And this is the story of Glenn Rodriguez, who was sent to prison for a crime he committed as a kid. And then he was denied parole like 17 years later. And why is that? It's because someone had incorrectly entered some information into a black box predictive model that was being used to predict whether he would commit a crime in the future. And after the parole board hearing, when his parole was denied, he compared his score sheet to someone else's and noticed an error in his criminal history features. And so this is a case where the parole board didn't really make a decision. It was really a typographical error that made a decision. And the model, the proprietary model had 137 factors in it. So, or up to that amount, we don't really know. So that it wasn't really that easy to spot an error. Now, the same situation probably happens to a lot of people with the same model and to other people with other models. But the point is, it's very difficult to spot the error because the model was proprietary. And what else might go wrong with black box models? Well, if you lived in California during the wildfires in 2018, you've been using Google's daily air quality predictions to determine whether it was safe to go outside. And you might have seen Google's predictions that air quality was fine on days when people were also seeing a layer of ash on their cars. Because during the wildfires, Google replaced the Environmental Protection Agency's Trustworthy Air Quality Index with this proprietary model from this company, Breezometer, which claimed to be more accurate. But the proprietary model wasn't doing what it was supposed to, and it put a lot of people in danger. And so it's another issue with these black box models is they're difficult to understand and troubleshoot. Here's another example of something that has gone wrong because of a black box. You could receive worse healthcare because of your race. So this article said that a hospital was ranking patients to get additional attention, and the white patients got higher rankings even if they weren't sick and as sick. And it's because the algorithms were using cost information to predict who should be given care. And the black patients were receiving lower cost healthcare. And the algorithm thought they were less sick because the cost was lower. And so it didn't recommend additional care for them. And that's just the tip of the iceberg. I'm just giving you a few things that have gone wrong with black box models, but there's a tremendous amount more that could go wrong. And probably many things have gone wrong that I don't know about because they were all, hidden and so on. And now people are starting to use machine learning for medical decision-making, for loan decisions, for self-driving cars, and for all manner of other things that you really don't want to go wrong. And some people love their black boxes, right? They argue fiercely that they need them, that you're going to be more accurate when you use a black box and so on. Anyway, so what's an interpretable machine learning model? It's a predictive model that is constrained. It obeys a domain-specific set of constraints that makes its computations easier to understand. And I should mention that there is a spectrum between fully interpretable models where you can understand how all the variables are jointly related to each other. And then on the other end are like these loosely constrained models where like the model has to decrease along one variable, for instance. Now, we can use interpretable machine learning even in very high stakes settings. So I'm going to give an example where interpretable machine learning is used in the highest stakes settings that you can imagine, which is the care of critically ill patients. So let's say that you have an aneurysm and it bursts, which means that this is a blood vessel in your brain. It bursts, there's blood in your brain, you have a hemorrhage. You go and you get surgery and you're placed in the intensive care unit of a hospital and you're being monitored with continuous EEG monitors. There are monitors all over your head, and they're monitoring like electrical signals in your brain. And the reason that they're monitoring you is because you might get a seizure in your brain. These are subclinical seizures, which means that you're not shaking, it's all in your brain. And those seizures are common. They occur in 20% of such patients. They cause brain damage, they cause death, And the only way to detect them is to have the patient be monitored with EEG. Now, in seizures, I should say, they can actually be more problematic than the original injury, like the original whatever you had. Now, so we need to predict these seizures in advance, because that's how the doctors know how to care for the patient. They have to put the patient on medications, and they have to keep the patient monitored for as long as the patient needs to be monitored for. But I should also mention that EEG monitoring is expensive, and it's also very limited. There's not enough monitors often to go around. There's not enough doctors to watch those monitors. So in any case, we have to allocate the monitors very carefully. We don't want to keep the monitors on patients way too long, which would deprive other patients of monitors they might need. Okay, so we got to predict these seizures in advance. And so we worked with clinicians, neurologists, to create a model called the 2 helps 2B score. And you're going to look at it and you're going to say, I'm not sure that's a machine learning model. She's just showing me something that somebody made up. But no, it's actually a full-blown machine learning model. It's an interpretable machine learning model. And the model looks like this. And this is, like I said, it looks like a rule of thumb, but it's actually a full-blown machine learning model. It was not created by doctors. It was created by data fed into a machine learning algorithm. It is a full-blown machine learning model. It's the optimization problem. It happens to be just as accurate as any black box model that you could apply to this data set that we built it from. And the nice things about it are that, doctors can choose for themselves whether to trust it. It's not like a black box where it forces you to trust it. Here, the doctors can look at it and say, like, I'm not sure I agree with that. Maybe I should, I don't like it. I don't want to use that model. And also the doctors can calibrate the score with information that's not in the database. So for instance, if a doctor looks at a patient and they see something about the patient that's not in the database, they can use that information to say, well, I'll give the patient 2 extra points for that. Now, our database that we built 2 helps 2B from, 2 helps 2B is only like 6 variables, but the database we had was over 70 variables. So the algorithm had to choose which of these variables were right for this particular problem. Now, as I mentioned, the 2 helps 2B score solves a mathematical problem. And I'm going to put the problem up just in case there are any of you who actually like to see math problems here. But in any case, what you'll notice is that there's a term to keep the model accurate, which is a logistic loss term. There's a term to keep the model small, which means use as few variables as you need, but keep it accurate. And then all of this stuff down here means make the points integers. So you get 1 point for this, 2 points for this, and it could go up to 10 or down to -10, but it shows just 1s and 2s. And if you are a mathematically inclined person looking at this slide, you might say, but you can't solve this. This is really hard. This is actually what's called a mixed integer nonlinear program. It's very, very difficult mathematical problem. But my point is that this should be a problem of computer scientists. It should not be a problem that doctors have to solve themselves with the database. It should be something that we have code to solve. Okay, so now what happens is the patient with their burst aneurysm comes in, gets their surgery, they're monitored with this CEG monitors. The neurologists look at the EEG and they say, okay, this person has a point for this, a point for that, and a point for this. That's a high-risk patient. Their 2 helps 2B score is 3. I am going to now place the patient on continuous monitoring for at least 72 hours and start them on preventative medications. Now, so far, the 2 helps 2B score has been independently validated, which means that there was a data set that it was validated on a data set that's separate from the data set that it was built from. And it had over 2,000 patients in that big data set. And it held up very, very nicely in that its behavior was very similar on the patients we trained it on, the patients that it was validated on in this independent data set. It's been implemented at several hospitals, and so far it's resulted in a huge reduction in the duration of EEG monitoring per patient, which allowed the doctors to monitor a huge amount more patients than they could before, over twice the number of patients that they previously had monitored. And according to the doctors, this number, this 2.82, is really important because it allowed the doctors to find patterns that they wouldn't have found before and help reduce brain damage and help the doctors save patients' lives. It's led to millions of dollars in estimated savings. That's probably an underestimate, but in any case, the fact that the important number is that 2.82. Now, you wouldn't have been able to do this with black box models, not nearly at the same level. You wouldn't have been able to get it into practice. You wouldn't have been able to convince doctors to use it. And in fact, there's good reasons why doctors wouldn't really want to trust it if it was a black box. Okay, so that's how interpretable models are supposed to work, but don't they lose accuracy over black boxes, right? This is how interpretable models are supposed to work. Don't they lose accuracy over black boxes because they're constrained to be interpretable? And you'd think they would be less accurate, but it's not true. And I'll give you an example. So here is we'll go back to Glenn Rodriguez that we talked about before. And was just wondering, like, how accurate is that fancy proprietary model that's used in the justice system to make his decisions, right? How accurate is that model? Well, luckily there was a data set that was released from Florida a few years ago that had information about each individual who was scored, and it had the COMPAS scores associated with it. So we could actually test how accurate it was in comparison to interpretable machine learning. So we took the COMPAS scores and we compared them to the scores from predictions from an algorithm that was like the most recent algorithm coming out of our lab. It's called Corals. Corals is an algorithm that produces little tiny if-then rule-based models. So we said, all right, we don't know how well this is going to work. We'll take the data from Florida and send it into our machine learning model and we'll see what we get. And we got a model that was so tiny that I can fit it on the bottom of a PowerPoint slide. So here's the model. It says, if the person is between 19 and 20 years old and they're male, predict arrest within 2 years of their COMPAS score calculation. Else, if they're 21 or 22 and they have 2 to 3 prior offenses, then predict arrest within 2 years of the COMPAS score calculation. Also, if you have more than 3 priors, predict arrest. Otherwise, predict no arrest. Okay. So if we looked at this model and thought, oh my gosh, there's no way this model can be as accurate as COMPAS, because COMPAS was written by a company that has a lot more data than we do. And there's just no way. But as it turns out, we were wrong. The two models were almost identically accurate. The colors here are different folds of the data. There are 10 different folds. And you can see that the accuracy scores between these two are almost identical. And we were shocked and thought, okay, well, let's just throw the whole machine learning arsenal at this problem and see if we can get any more accuracy. So we applied every machine learning tool that we had, well, maybe not everyone, but a whole lot of them. And a lot of these are black box models, by the way. Like, this is boosted decision trees, which you can't fit on a PowerPoint slide. That model would be like a whole bunch of trees that are combined in various ways. This is support vector machines with radial basis function kernels. So again, you just can't, these are not things you can put on a PowerPoint slide because the formulas are so complicated. Whereas on the other hand, a model like the Corals model is so tiny that, again, it's sitting in the bottom of the PowerPoint slide. So there was this huge debate, by the way, about the algorithmic fairness of COMPAS as to whether it was fair. But the truth is we just don't seem to need COMPAS at all. So, why are we still using it? Now, I want to add a little bit more nuance to this thought I provided that interpretable models are as accurate as black box models. So it seems to be true that for tabular data problems, you can get these really tiny little models that are just as accurate as the black box models. So tabular data is kind of like this, like where you have just different features, and then you have a number or a category associated with each feature. That is compared to raw data, like what I call raw data, which is where you've got images or sound waves or large amounts of text. Like if you look at one pixel in an image, that's not really going to tell you anything about what's in the image. Whereas if you know things like whether someone smokes, that tells you a lot about medical outcomes, for instance. So these two types of problems are very different from each other. Now, for raw data problems, the only technique that's really working right now is neural networks. And that doesn't mean that you can't still have an interpretable model. In fact, we design interpretable neural networks in my lab. But for tabular data, as I said, you often have this situation where with minor pre-processing, all the methods have very similar performance. So just like I showed you with the example with compass and corals, that happens all the time. And so it opens up an opportunity where you can have very sparse models like decision trees or scoring systems like I showed you, like trees like the corals model or scoring systems like the 2 helps 2B score. And it opens up opportunities to use those types of models without losing accuracy. So it really gives us an opportunity to create really, really simple models. So I want to just kind of briefly talk about I know I'm running out of time. I've got about 5 minutes left. So I'm going to use that 5 minutes to talk about my first real job, which was to rank all of the manholes in Manhattan in order of their probability to explode. that was actually my job. I'm completely serious. I did this job for 3 years, full time, in order to help the power company in New York. So these are called serious manhole events. That's what they're called at the power company. And these are fires and explosions and smoking manholes that can be really serious. And about 1% of the 53,000 manholes in Manhattan have some kind of serious manhole event each year. And most of these events are caused by breakdown of the insulation around the underground electrical cables. And salt from the street is part of the problem. Like, but the salt seeps into the manholes and it disintegrates the insulation around the electrical cables. And so that's what causes short circuits, causes a pressure buildup, and then that's what happens. And I like this picture a lot because, like, you can see that nobody wants to get near that thing. Just, you don't go near that. Anyway, so as I mentioned, I worked on this for quite a while. And what I'm showing you here is an overhead view of just a random street corner in Manhattan. And you can see that there are a large number of manholes that go down every street and every avenue, which they're all labeled here. And the colors on this plot are showing the vulnerability ranking from our manhole vulnerability model. And the data that we had to work with was just crazy. I mean, it was just insane. And it included accounting data from all the way back to the 1880s. And some of the data were text documents. So we had data about the cables. That was the data from as far back as the 1880s. We had data about the manholes, how big they were, whether they were a service box or a manhole. We had events data, which is like, if your power went out or something like that. And then we had inspections data from a brand new inspections program that Con Edison had just started, which we were helping with. So I want to show you some of the event data, because that data was our most important data, because we were trying to predict events, but it was very difficult to work with. So yeah, I get a headache just thinking about how difficult it was to analyze this data. My collaborator, who's an expert at natural language processing, says this is not natural language. And I can tell you exactly what this ticket means now. I know all about how to read these things now, but I think maybe I'll spare you with what it actually means. But it does involve a very interesting story about an engineer going to a manhole and finding the cable melted onto the duct between the manholes and calling in a flush truck, which sticks a big tube in the manhole to suck up a lot of gunk in the manhole so you can see what's going on. That's what it actually says here. Okay, anyway, so I tried what any machine learning researcher would try. And keep in mind, this was before the term data science existed, right? There was no data science. There was no big data. It didn't exist back then. And so anyway, I threw the data into this black box, kind of expecting magic, but that didn't happen. And in fact, all the machine learning methods performed the same, and none of them performed very well. And in the end, after years of struggling, we picked ourselves up off the floor and constructed a model in which we understood every aspect of what was going on. We knew, we pulled out data from those trouble tickets, we pulled all the data together and made these beautiful models. And then we asked Con Edison to blind test us. So we told them, you withhold some data from the database, don't give us the most recent data. And then we made predictions, and then they evaluated those predictions. And here is the result. This is the result that we did in the Bronx. And so there are 27,212 manholes in the Bronx that were ranked by our model in order of their probability to explode or have a fire or a serious smoking manhole. And this is our ranked list. And if there is an arrow with an X, it means that manhole exploded that year. And then if there's an F, it means that the manhole had fire in that year. And again, this is a blind test, so we didn't get any of the data from that year. What we found was that within the top 10% of our ranked list, we were able to capture 44% of the manhole events that happened that year. So what that means is that if Con Edison had inspected the top 10% of our ranked list, which is very doable, then they could have reduced the number of manhole events by up to 44%. So in this project, it really, this project was actually the reason I went into this field. It changed my career, working in the real world and realizing that, if you don't understand what's going on, you're probably not doing a very good job. So it's a case where, we sort of ran up against a wall and then, designed models that were actually interpretable and were able to finally get good performance. And the key lesson from this is that what people call the accuracy interpretability trade-off is actually reversed. So a lot of time people talk about an accuracy interpretability trade-off where you get worse prediction, you get worse predictions if you can understand what's going on. This is kind of the traditional accuracy interpretability trade-off image. This, by the way, this image is made up. It's not associated with a real problem. This image was taken from the DARPA Explainable AI BAA. But in any case, it's supposed to show that there's an inverse performance with understandability and accuracy. This is actually, it's the opposite. The more you understand, the better job you can do actually designing a better method and handling your data better. And also troubleshooting your model on the fly so that you don't make typographical errors and you don't send people to prison accidentally. Okay, so just to summarize what I've discussed, predictive models are everywhere now. They're in, they're in all of our major systems. And, don't we want to be able to troubleshoot them? Don't we want to detect if they're biased in a harmful way? Don't we want to be able to ensure that a typographical error didn't make a decision for us because we entered some data incorrectly into a complicated model? Don't we want to be able to use these models in high stakes decisions like predicting seizures in critically ill patients or loan decisions? Don't we want to be able to understand what these models are doing just so that we know what we're doing is that we're on the right track? All right, thanks very much. I put up a slide here. A lot of people have been trying to sort of explain, they'll run a regular neural network and then they'll try to explain it by creating what's called a saliency map, which is a highlighting part of the image that the neural network is paying attention to. And I really was kind of unthrilled when saliency maps started to be called explainable, explaining a black box, because they don't really explain a black box. So for example, this is an explanation of why this animal is classified by our neural network as a Siberian Husky. And you can see it's sort of highlighting the correct part of the image. Okay, so you think, okay, well, I trust the network, it's doing a good job, it knows what it's doing. But the truth is it doesn't. So this is its explanation for why this image contains a transverse flute, which is a musical instrument. And so, it's really not, it's really not, necessarily thinking the way you want it to think, right? Okay, and I should mention there's lots of work in radiology on attention maps right now, which makes me very, very scared. the attention value where the network doesn't tell you what it's doing with that information. That's like your real estate agent saying, you say to your real estate agent, why did you price my house like that? And the agent says, because of your roof. And you say, what about my roof? And the agent just says, no, it's because of your roof. It's just look there. Anyway, so we were wondering, like, if we could create an inherently interpretable, deep convolutional neural network for computer vision with the same accuracy of the black box. And if I could do that, maybe you would believe me that we don't need to explain these black box models. Instead, we could actually design models that were inherently interpretable. So again, interpretability means constrained. So you'll see that it's constrained to reason in a certain way. Okay, so this is my network explaining to me why this little bird is classified as a clay-colored sparrow. And this is the network explaining what it actually is computing. So the network is going to highlight different parts of this bird and tell me that it is doing a comparison between this part of the bird and this other part of that bird. And this bird is a prototypical clay-colored sparrow. And this comparison here to the edge of the wing and the belly, that is a comparison to this other bird here. And it's what the network is doing is it's giving points for each comparison it makes, and it's going to add up all the points. And it's going to do that for each of the different classes of birds. So let me give you a little bit more detail how the computation works. Oh, by the way, because the network is saying this looks like that, and this looks like that, and this looks like that, and that's how it's computing, we call the paper this looks like that. And so what the technique does is it allows you to start from your favorite black box deep neural network, and it adds a layer to the network called a prototype layer, which forces the network to do this sort of case-based reasoning, where it forces the network to reason about how similar things are to other things. And the prototypes and everything, all of that stuff is learned during training. So I'm just drawing a picture. This is a kind of a standard picture of a deep convolutional neural network. And then in the middle of the computation, well, toward the end, really, we add this prototype layer that tells the network to make these comparisons. So I'm just going to zoom in on this sort of computation over here to show you what's actually going on. So here the network is telling us why this bird is classified as a red-bellied woodpecker. And the network says, well, I think this part of the image looks like this part of that image. And I'm going to give it a similarity score of 6.499. So it gives it a score of how similar this is to that. And then there's another number over here for each comparison, which is how important this prototype is to this class. So these are all prototypical red-bellied woodpeckers. And there are 20 of them for each class. So there's like 20 pairs of numbers for every prediction. And so that tells you how many points you're getting for each comparison. You add up all the points, and then you get a total number of points for this red-bellied woodpecker class. And it does it for all the different classes too. So for instance, if we say, well, what's the evidence for this bird being a red-cocketed woodpecker? Then it would make comparisons and add up the points. But see, the thing is, apparently red-cocketed woodpeckers don't have red heads. And so the network's it's doing its best to sort of like compare with the similarity on the feathers, but it can't gather the points it could get because of the similarity of the heads. And so that's why it only gets 16 points, whereas here it gets 32 points and says, oh, this is a red-bellied woodpecker. And we've been doing experiments with this bird data set. This is actually a benchmark data set in computer vision where, the deepest of the deep neural networks are compared against each other, the fight to the death, right? And our network fared really well. The original black box accuracy was between 74% and 82%. And I've just listed the names of the black box neural networks that are here. And when we applied our technique on these black boxes, we got accuracy within the same range. So it's just, we're not losing accuracy because we're interpretable. But when we took our interpretable neural networks and put them on top of each other, we still got a network that's doing case-based reasoning, so it's still interpretable, and it got us an accuracy that was better than the black boxes. So, we're still not seeing any evidence. We're really not seeing any evidence at all that you have to lose accuracy when you have deep neural network. So even for computer vision, we can still have an interpretable model of the same accuracy as a black box model. So we've been trying to apply this technique to mammography because we created the technique and I was like, okay, what do we do with this? We've proven that it exists. Now what? So what? And so we decided to try to use it for a medical problem. And I reached out to a colleague of mine called Joseph Lowe, who was helping us with this. And he and I have been working together with our students to try to get this method used in mammography. So mammography, as you know, is for breast cancer, which is the leading cause of death in the USA. Hundreds of thousands of cases diagnosed each year, causing tens of thousands of deaths. It's the hardest task in all of radiology. Humans have a lot of trouble with it. Radiologists miss a fifth of breast cancers. Half of all women getting an annual mammogram will have a false positive, which means that the radiologists are seeing, they're seeing things, they're calling people in, it's false positive. Up to 3/4 of biopsies come back as benign. In other words, potentially unnecessary surgery. So we thought, maybe this is something AI can help with. Now, an uninterpretable approach, which is what most major radiology companies are sort of pursuing right now, is that you take this thing, the image with the lesion in it, you send it into the AI, and the AI says, it's probably benign. The probability of malignancy is low, no reason. Now, the people who claim they're doing explainable machine learning, what they're doing is highlighting the part of the image that they're creating a saliency map, right? Just like I was showing you. And so it says, okay, the probability of malignancy is low, predict benign because blob. Thanks a lot. I don't know what to do with that information. You're not telling me what you're actually doing with that blob. And so our network does something different. It takes the image, takes the lesion, and it picks out parts of the lesion and compares them to prototypical lesions with different mass margin types. So it says, well, I think this part is a bit indistinct. It looks kind of like this prototypical indistinct margin case, whereas this part is circumscribed. Circumscribed makes you less likely to be malignant. And so it actually creates a score for the indistinct class and circumscribed class and adds those scores together to get an overall prediction of malignancy. And so basically the whole pipeline is that the radiologist gets a region, gets this sort of thing that they're supposed to analyze. It zooms into the lesion, fetches similar prototypes, calculates the comparison scores, and feeds the scores from each of the mass margin calculations into, just puts it there for the radiologist to look at. There's an overall score of malignant versus benign, although the radiologist doesn't really need that because they're actually just trying to figure out whether to give the patient a biopsy. And if you have more than a 2% chance of being malignant, then the patient goes to the biopsy. But essentially, the point is that the radiologist doesn't need to trust it. It's not like a black box. They're not forced to trust it. They can actually look at what the comparisons were and decide whether they agree with it.